Good morning and welcome. I'm Brent Donaldson, Senior Editor for Modern Machine Shop and for Additive Manufacturing Magazine. Today's webinar, brought to you by Emag, details how unique characteristics of shafts create different challenges to that of cubic or flange type parts. Today, Emag will explore different technologies required in the manufacturing flow of shafts, as well as unique solution that Emag offers to address some of these opportunities. Today's primary topics will also include unique shaft production solutions and technologies required for production of shafts. Today's presenter is Kirk Stewart, Emag's Vice President of Sales. Now with 15 years of experience with the company, Kirk started out representing the high-end, high-complexity sales of crankshaft grinding, with responsibilities that have evolved to cover the Emag Group's entire product portfolio across the United States. Please note that you can submit questions for Kirk at any time during this presentation using the chat box, and that's the questions box, and we'll answer as many as we can at the end. Also note that this webinar is being recorded and you will receive a link to that recording via email. With that, I will turn it over to you, Kirk.
All right, thank you very much, Brent. Thank you everybody for joining today. Hopefully it won't take too much of your time, maybe about a half hour, and then some questions after the fact. So as Brent said, I've been with Emag for a long time. I've seen a lot of things. Here on this front landing page, you see a lot of the technologies, many of which have been brought to the Emag Group through the years. So, I wanted to choose the topic of shaft production because I think it is a little bit different. If we speak about our world of machining, there are two quite discrete groups of machining. You have your prismatic machining with all of your milling type applications, the true cubic work, and then the other family is comprised of all the round parts. And even within the round parts, I think there are different challenges and different solutions that are differentiated between shaft type parts and flange type parts. So I wanted to go through those today and just kind of discuss some of the challenges that are faced with shafts more so than flange components. And some of these things will overlap and some are more critical than others, but just kind of speak about a few of those things. Speak about the technologies that are on and required for shaft processing. Same thing, many of these things will apply to round flange type parts, but some are a little bit more discrete. And then share a lot of the solutions maybe that Emag has unique capacity to perform on. So what are we talking about when we speak about shafts? All the shafts in this picture are kind of what I'm focusing on today, be it a pinion shaft, a tulip shaft, a drive shaft, a crankshaft, shafts. We speak about rotating components in their application, and that also, impacts the machines and the technologies that we focus on. But it's this family of parts, talking down to the 3-inch size part up to, let's say, 36, 40 inches. That's kind of what I'm focusing on. What I'm not going to be really addressing so much today are the big shafts. And big shafts are a totally different conversation. The upper left picture is a mill turn machine from WFL, great machine from Austria. I think we are all going to miss going to IMTS in the back of the hall and seeing their crazy component and all the different types of features that they can mill turn. On the bottom, we have a picture of a crankshaft grinder. I think this is one of our, let's say, less known solutions within the Emag portfolio. We can grind cranks, pins, and mains up to 6 meters in length. And again, these large shafts, they simply outside of the discussion today, but definitely have their own challenges. And likewise, I'm not going to focus on, the flange type parts. Some of these things that I'll speak about do overlap here today for sure, but really focusing on shafts. So what's unique about shafts? I would say first and foremost is this length to diameter ratio. A long part with a small diameter, in the most extreme case, is the most challenging part to process, and hold that part end to end and maintain a run out and a roundness and a straightness. It just gets a little bit more challenging giving those long length versus what a smaller diameter can get you. And that's not to say that there aren't robust, stiff, stout little shafts out there, but a lot of them are a little bit more wildly than others. Unique in shaft manufacturing is the fact that you have to have some sort of ends preparation. If we do contrast these parts to, a standard flange type part, when we begin the process, you have your side A turning, your side B turning, and off to the races you go. Whereas with shafts, you have to always start with the centers. The centers and end facing tend to be the very first operation and do require, additional capital, additional processes that need to be integrated into your flow. There are instances where parts will have forged centers, obviously with some sort of quality trade-off. So be on the lookout for forged centers. In some cases, they definitely make sense, but more common than not on shaft parts, you are going to have a machine centers. Steady rest, this kind of goes back to that length diameter ratio. If you do have a long part, you really can't be 8 times more than the diameter away from work holding, whether that work holding is the center itself, the chuck, or in the case of the steady rest. So steady rests are, again, not necessarily required for a stout little flange type part, but certainly unique in the world of shafts. Going back to centering, very challenging to deal with these, more so from the fact that your final part print, as it's designed for that component to go into assembly, 9 times out of 10, the centers are absolutely insignificant to the function of that component. However, in many components today, those centers are the datum structure from that Op10 process through your finish polishing or grinding operation. So you do have to be very aware of what the tolerance stack up is to your centers, because ultimately those centers, once that component is assembled in whatever it is, a gearbox, this, that, or the other, the quality of those centers as it relates to a journal bearing or some other feature, really it goes away. So you do have to take care of your datum structure and your tolerance stack up to your centers. Different technologies on shafts. No doubt this is kind of where we definitely do run into overlap with flange parts, whether we're adding a hobbed feature onto the component, doing additional milling, perhaps hardening the component. Those things do overlap, but let's address some of the technologies with shafts specifically. And going back to big parts, we're not gonna use too many VTLs out there for big parts. There is one solution within the Emag group where we do have a VTL, in fact, with a tail stock to support the component, but that's limited on length. So you get up to those larger parts, not a lot of VTLs are going to be able to deal with those longer parts as we go. So let's talk about machining the ends. Anytime you have a shaft, you do have to start with putting the centers in at a minimum and milling the end face and putting a center in. So you do have different options. Certainly a very traditional solution is to, throw your part onto a table into a milling machine. The benefit of a milling machine is, most shops have excess capacity on their milling machine, or they have those assets that they can redeploy very easily to do that ends prep. Depending on what that shop is looking like, what the environment is, what the batch sizes are, this might be the perfectly adequate solution. Nothing wrong with going with the milling machine, and in the big scheme of things, a rather inexpensive solution. If you get into more of a high volume type application and you really need to spit out a lot of parts, then you can look at some more unique solutions to shafts. In this case, what I'm showing here is a center drive machine. This is definitely geared, towards two things. One, it's going to be very fast. I have a turret on the left-hand side and a turret on the right-hand side, and I'm turning those features. I can thread the external features. I can drill through the center. I can use live tools on the turret to maybe mill some features. But the big benefit is you're doing those things simultaneously. The other big benefit is quality. In this case, you're clamping on the component and you're turning this thing at a high RPM, And that gives you a really nice quality benefit. It means your quality relationship from the features that you're turning on end A to those that you're turning on end B should be very good in relation to each other. And as I said previously, since centers largely are not used in the final application of the component in the assembly, it is really good to have good centers. You do have to have a relatively good incoming component. If you're working with tube stock, that's a great opportunity to use this type solution, or a near net forging type application as well. So there are different solutions out there. Emag comes into the mix with our VTC250 Duo ED. I know that's a mouthful, won't get into the nomenclature. But this machine, I'll show you a video in a second, basically features a rigid fixture in the machine in the first station, and then a 4-axis turning station in the second station. So the big benefit is you're getting the turning and the centering in one machine. So once the video gets going here, what you're going to see at the front end is basically a carousel, which is going to house the raw parts coming in. This is featured on almost all Emag machines out there, and really works with the principle of loading up the carousel and walking away. So in this case, I'm only showing 6 pallets, but this could very easily turn into 12 or 18 pallets. And if we have, let's say, 12 pallets and a 1.5 minute cycle time, that's 18 minutes of true walk away time. So you see that my turret here, we call this one on the left our big elephant's foot, had a gripper on the back side of this turret. The front side, it has all the milling tools, the back side has that gripper. And this also fits into Emag's principle of machine design. We always want to be self-loading, use the machine to load itself. So not only are you buying one machine to do the turning and the milling, you're also getting the automation for free. So you can see that we did the machining of the top half of this camshaft, we milled the face, we drilled it, and we also put a hollow mill in there, which is going to be my clamping diameter for my next station for the turning. And then I moved my fixture up and my elephant foot turret down, and I did the same operations plus the threading of the ID here. So what you're going to see next is the middle turret. I have 3 turrets in the machine. It's going to transfer the part to the next station. Now, video is not harmonized perfectly, but all these operations are happening quite seamlessly. So now that I've transferred the part to my second station, now I'm doing my 4-axis turning. I've got a 3-jaw chuck. Maybe sometimes I'm using retractable jaws. And by using 4-axis machining, I really have the ability to reduce my cycle time. And 4-axis machining isn't always required in regards to the volume outputs. There are a lot of shops that don't utilize 4-axis turning, but I think there's a lot more opportunity on the market for more users. At the end of the day, we want to make more parts more quickly. That allows us to make more dollars in a shorter amount of time. So all Emag shaft machines are 4-axis machines, and in some cases, as I'll get to a little bit later, configured a little bit differently. Another way to, went too fast there. Another way to process the ends of your component is to use one of our standard machines. What I'm showing here is a VT. This is one of our standard machines that we have in our lineup, and you see 2 raw parts coming around. We have a carousel, maybe there are 20 parts in there. Again, let's say we have a 1-minute cycle time. That's 20 minutes of walkaway time. So in this case, I have a heavy-duty gripper on my turret on the left, and I'm actually going to hold that part while I do the milling and the centering of that component. Now, to be clear, I'm not taking a huge heavy cut. There's only so much that that heavy duty gripper can do, but you see the same thing. I do my face milling, my centering, and also the hollow milling so that I can clamp on a qualified diameter like I'm doing right now. I hold the part, now I'm dropping my turret down. I'm going to now regrip on the shaft at the bottom side of the component and repeat the process to mill the face, put the center in, so on and so forth. So in this case, my part is static, and I'm using live tooling on my right-hand turret so that I can do the milling and the centering work. Now I'm going to drop the part onto the center. You see my steady rest is moving on its own axis as well. Advance it to both centers, engage with my 3-jaw chuck, and now I have the ability to go in my 4-axis. So same thing, I have one machine which is prepping my ends and also doing my 4-axis milling, and it's loading itself. In this case, we're not turning the complete length of the shaft, but it's a great solution, you know, especially if you don't have such a high volume. The cycle time being additive, milling, centering, plus turning, you know, even if that cycle time adds up, you know, if you're not making 400,000 parts a year and you're in more of a small shop environment, this is still a very interesting solution. Set your machine up, load the raw parts up, and off to the races you go. So let's talk about grinding. Again, you know, we get into grinding and we got to talk about centers and the critical nature to the datum structure. Here again, we have different solutions. So shafts, one of the great solutions in the grinding world are centerless grinders. Centerless grinders are very robust, very predictable, very good quality, and very fast as well. You have a master-slave wheel type configuration, and you're removing material, the part from 2 wheels. So again, it's very fast. Brings a lot of benefits on the machine side as well, especially here in the North American market. These carcasses of machines are rebuilt over and over and over, upgraded for controls, and there's a lot you can do with these machines. I would say especially in smaller components, high volume small components, centerless grinding is a great solution. There are other more niche solutions out there, and again, this is kind of where we go, but you know, in between we have more of a universal cylindrical grinder. This one's shown from the Akuma side of things. They have a lot of machines here in the North American market. They got a great price point, and they also offer very easy setup, very flexible programming, very easy to use, and still has the quality to be a production grinder as well. Lots of other universal grinders out there, you know, from Kellenberger, from Shout, you name it. There's a lot of different solutions out there that are going to give you that flexible cylindrical type solution between centers. Emag and others kind of come into the field where there's a little bit higher demand for the production rate and quality. A couple examples that I'll show you here. The one on the right is for a locomotive camshaft, and this is a single slide B-axis dual wheel machine. So in this case, we have 2 different wheels. One is specific to the journal grinding, and the other one is specific to the lobe grinding. There are lots of grinder companies out there with lots of different solutions. In some cases, you can see that configuration on the wheel side duplicated with an additional slide, an additional two wheels. Sometimes you can have 3 wheels on each side, so a 6 wheel grinding configuration. No doubt with all that additional flexibility, there does come a price premium, but really if you have that product and the volume mix, this and that and the other, there's nothing wrong with that. Again, there are a lot of other players out here in North America, American company, pat them on the back. Weld does a great job. But you know, we come to those production type solutions. So this one's a little bit unique. This is a drive shaft, and it has a unique datum structure that requires that the ground features are relative to the pitch line of that primary gear. So we're using our integrated gantry to load the component into the center drive. Spoke about center drives previously in regards to the ends prep. In this case, we're going to use a center drive for the component so we can grind both sides. So we bring in a Marpos gauge to establish the length, and then we are going to be grinding the face and 4 different diameters. I'm going to advance my steady rest here and disengage my end support. That steady rest is to support the component during the grind and get the other support out of the way. In parallel, and at the same time, we have an internal grinding wheel. Again, datum structure is going to call everything back to the pitch line, but the big benefit is here that I'm grinding both of these features simultaneously, so my cycle time is very low. So with a customized machine, customized for a center drive, customized to be grinding both features simultaneously. I've invested more, but my cycle time has gone down, so my output has increased as well. So there's a lot of different things you can do in that regard. So if we talk about all the full complete process chain, there's a lot going on. The ends prep, the turning, drilling and milling, hobbing. Starting with the drilling and milling, I would say the majority of our machines out in the market are utilizing live tools, and you likewise see that here in the video of the VT2 doing the same thing, ends prep, before we begin the 4-axis turning. I think live tools to a large degree in our market here are underutilized. Again, you have to have kind of the right production setup. I think Nakamura Tome does a really good job with live tools on their side of things. But certainly I would say the majority of the Emag machines in the field, we have some combined turning, drilling, milling type philosophy of our approach. So that VT's, our basic solution that we have for our shaft machines. After the turning, you have the hobbing, the hardening, hard turning, and grinding. And all of this results in opportunities to do more combined machining. So if we look at, too fast. So if we look at all those technologies, this is where Emag really stands out. If we look outside of any companies which might be machine tool conglomerates, I really don't believe that there's another machine tool company that offers the suite of products focused on round parts. We're not a small company by any means. As we've built up the technologies through the years, we really have the ability to perform on that mission statement of providing the best manufacturing systems for precise round components. So if we talk about hobbing, we have 3 shaft type machines, the K160, HLC 150, and the K300. This is one area where I'd say we really do a good job in job shops. Our hobbing solutions are used in those guys who have 12, 50 employees, smaller shops that have the low volume and the high product mix. It's just kind of the way the machine is configured, very easy input of the parameters to get the machine up and running, and at the same time offers the benefit of being able to load and unload itself, albeit with a integrated gantry, not the spindle directly. But we've really seen some of our customers transform their business. Not that there's anything wrong with an old Barber Coleman or Fellows machine. Those machines are built very, very well, and they're going to run unmanned for a really, really long time, but they are slow, and they do take a certain craftsmanship to keep going. We just recently installed one of these machines at a shop with about 20 employees up in Canada, and they had those old, green machines, and of the component that they were making, they could make 40 parts in 1 hour. 40 parts in 1 hour. With the Emag K160, they made 100 parts in 14 minutes. So it really shows you the benefit of bringing automation into your shop. From their standpoint, that's going to allow them to quote on more jobs, keep their manpower the same, and be more competitive in the process. Next step in the process would be the induction hardening. And I would say likewise, the LDEC solutions are geared around shaft type components. We really have solutions for low, medium, or high frequency type applications depending on the demand of the depth of the hardened zone. But we also feature simultaneous dual frequency, which allows us to achieve a true contour of a gear profile, as an example. So the second station here is doing the induction work, heating up each of the journals, and then the end bearing on this balance shaft. The hardening is happening here, and then the quenching. The next station on this dial type table is going to be the tempering station. This is really where you're tuning in how hard do you want to be. Do you want to be around 50 Rockwell, or do you want to be around 60? It's really the tempering station that controls that fineness of your final hardness. So once we get into the post-hard machining, we speak about grinding primarily. I'm going to show you a few different things here. I see my graphics a little bit pixelated. This is a rotor shaft, and rotor shafts clearly are becoming all the more relevant in this age. We just were awarded some business with an OEM out in California, nudge, nudge, wink, wink, for a very similar operation. So what we're showing here is a skiving operation. Skiving is an alternative to grinding in a lot of cases. You can achieve lead-free journals, especially when you have seal diameters, very critical. What's shown in the video, I'm actually utilizing my Z-axis to traverse down as well. But what's really interesting about scroll-free turning, if you look at the tooling on the left, you'll see that I don't have a standard single nose radius type insert. Rather, I have a blade at a 45-degree angle. So it's not so easy to say in the video, but basically once I engage that scroll-free turning tool, I'm also sweeping across the y-axis and interpolating down the z. So there's my skiving tool on the right-hand side. There's a very small sweep towards the y, towards the operator, if you will, and at the same time traversing down the z. The big benefit here is that you are putting the heat in the chip because you're changing the point of engagement on the nose or the corner of the insert through that entire length because I'm using my y-axis. You're not building up nearly as much heat into the insert, and thus the heat goes into the chip. When the heat goes into the chip, like we all should try to do in our machining, you are able to get better quality through the process. I speak about turning and grinding. You know, one of the things I didn't mention about the Emag machines yet is the fact that we have, you know, a cast granite machine bed. There are a lot of grinding companies that have cast granite machine beds, but very few do on the turning side. Well, Emag is very unique that all of our machines are with a cast granite machine bed, even our turning machines. So the benefit that is that we can have our basic turning machine turned into a grinding machine very easily. So with this cast granite machine bed, that gives us less vibration than a gray cast iron or a welded steel base. And when you have less vibration, your tool life is better on the turning side because you have less vibration. And you also have less heat buildup, which is critical on the finish side where you have tighter tolerances. You basically have a big rock as your machine bed, so less fluctuation, better vibration. You ultimately get better quality. So you just saw the turning side of this machine. You saw the same turret on the left-hand side loading and eventually unloading the component. But on the right-hand side, I no longer have a traditional turret. Rather, I've swapped that out with a CBN grinding wheel. You're also going to see that I'm going to utilize the turret as the carrier for my in-process gauge as well. So it's a BOGO. You get the grinding machine, which you need in your process, and you get the turning for free. So here I'm going to engage my grinding wheel. And there's my in-process gauge to do a little pre-measurement. I use it as a post-process gauge at the bottom. And this gives you a lot of flexibility, especially if you have lower volumes and you're spreading out different components on a machine. You know you need some hard turning, you know you need some grinding. This gives you the flexibility to play with those two variables to really come up with the best process in regards to quality and output. And rather than monkeying about from machine A as a lathe and machine B as a grinder, you can do everything in one. So if you put all of the things that Emag has to offer together, we have manufacturing systems. And again, this is where we are placed. No company has these technologies: laser welding, induction hardening, hard turn, grind, you name it. Everything you need primarily in the process we can perform on. Emag is also, you know, a sizable company. We're the fourth largest machine tool builder out of Europe. that puts us in pretty good company. So we have the horsepower not just from the financial backing to go out and purchase third-party equipment if I need a gear grinder, if I need a washing machine, if I need a polisher, if I need third-party automation. We certainly have the strength and stability to be able to do that financially. But we also have the engineering and the project management to help these large type customers where a system like this would be interesting. It means that we can be that sole partner of a customer rather than them going out to 15 different suppliers. They can place one order to one partner in Emag where we can take care of a project. So this line that I'm showing you is actually an e-rotor solution as well. It's made from two parts. This is the second part B, doing the op 20 turning. And the reason why that some e-rotor shafts are two parts then welded, which is the next operation here, is due to the nature of the need for a lightweight design. So by boring out those two IDs independently, then welding along the seam, you do get a lightweight component. After welding, we go on to one of our LDAC induction hardening machines to harden the journals on the ends. This is a T-configured machine with multiple stations, either for volume or for additional tempering. And then we go on to the hard machining side on the VT. So what I haven't demonstrated so well in any of my videos so far is our track motion. And this track motion is a really nice tool to bring parts from one Emag machine to the other. Kind of runs through a tunnel on the back side of the machine and transfers the parts from machine to machine. The big benefit is, as it compares to a lot of robot load, and do not misunderstand me, robots have their place, is that you can free up the operator on the front side to be accessible to the controller, to be accessible for tool change, and let the automation run in the background, serving other machines at the same time. So we've gone on to a couple of VL4s here for the internal finish machining. We passed over internal gear cutting, and now we're doing finish OD work with a little bit of ID work in there. And then the finish operation is going to be on a VTC250DS, again, a mouthful, where we are doing the finish grinding. This grinding configuration is one step further. In this case, I have replaced both turrets with two grinding wheel packs. So in the name of volume, this is kind of like a centerless, not exactly in this particular instance, but basically a grinding wheel on the left and a grinding wheel on the right, and I can grind the component all at once for that high volume output demand. So that's a little bit of everything that Emag can do in a nutshell. So in summary, respect the shaft. They can be challenging to work with, just that long length to diameter ratio. Take care of those centers. It's always going to be a little bit critical in your evaluation of setting up your operations, both on the front side for putting in those ends, and likewise concerning yourself with the datum structure and your tolerance stack up as it affects and impacts the final part print that you're delivering to your customer or putting into your assembly. And think about combining operations. It really is a unique solution that I think needs to be taken into consideration more so, especially as we all need to be more lean with our manpower, which means you need to find different solutions on the machine side. So if you can combine operations, you're achieving just that. And then I challenge you to think about solutions, system solutions. If you are in that group of manufacturers where you have limited resources and don't have all the engineers that you maybe did once at some point in time to manage your programs, we're more than willing to help out with either a full system or even a mini system can be interesting as well. So that concludes my presentation. I appreciate your time, and certainly if there are any questions, we can do a little Q&A at this point.
All right, thank you, Kirk. To our live audience, just a reminder that now is your opportunity to ask questions. Just type them into the questions panel and we'll do our best to answer them. In the meantime, we do have a couple of questions in the queue, and let's start with this. Do you have a solution for grounded shaft or turbocharger wheel for passenger car applications? Can we replace grinding applications with hard turning?
Yes, so in a lot of cases you can do exactly that. I would say that it is still more common to grind the assembly post weld. We have some customers which are assembling the turbine head to the shaft, typically with welding technology. There are different competing technologies, whether it's friction welding, e-beam welding, or laser welding. Commonly after that, there can be an induction annealing process to take care of that joint, which has created some unwanted hardening. And after that, there are different solutions. I've seen some customers do hard turning. Some use hard turning just as a preparation for finished grinding. At the end of the day, it's about the tolerances and the demand. I would say it's something we can definitely look at in regards to just a hard turn solution.
Yeah, the same audience member kind of followed up and asked, or a combination of hard turning and grinding on a single machine for turbocharger shafts.
Yep, absolutely.
All right. We do have somebody wondering where the 3-to-1 ratio originated and making a comment that large American machine tool manufacturing used to be a 4-to-1 ratio. Just more of a comment than a question, I suppose.
Yeah, I would say it's a rule of thumb, and every component's going to be a little bit different. Do you have a hollow component? Do you have a solid component? Is it thin wall? Is it solid? Every component's got to be a little bit different as you evaluate it. One of the nice flexible things in the Emag lineup is that our steady rest is on its own axis. So if you do have those longer parts, you can stitch your steady rest to different support areas along those longer shafts. And that contrasts with a lot of solutions out there that have fixed steady rest. We're not alone in that, to be clear, but all of our steady rests are on their own CNC axis.
We have another listener asking, where does hobbing with live tooling lathe benefit over traditional dedicated hobbing machines?
So you got to be careful when it comes to adding live tools on a lathe for your hobbed feature. It has a lot to do with your quality requirement, and a lot of the hob solutions out there are not going to give you the quality that you would get off of a traditional dedicated hob machine. So the best application for using a hob head, a live tool hob head on a lathe, is when you're looking at splines. Splines are a really good opportunity, rather than, having a spline roller as an additional operation. If you have the cycle time flexibility and you don't have that high volume demand, hobbing a spline onto the component a lot of times can be a good solution. The other challenge of using live tools on a lathe is the shift length. A hobbing machine has a long shift length, which means your hob can have much longer life. Whereas with a lathe, you have to look at your y-axis stroke, which is effectively going to become your hob stroke. You don't want to be changing out your hob all the time, but every manufacturing environment is different, and each one needs to be evaluated separately.
We have an audience member wondering if you offer Fanuc CNCs on any or all machines.
Yes and no. So all of our turning machines and some of our turn grind machines have a Fanuc control. So let me restate that once more. Our standard turning machines, our standard control is in fact Fanuc. If you would like a Siemens control on one of our standard turning machines, we can perform on that. It is a little bit of a premium option. When we get into more of the specialized machines, speaking about a crankshaft grinder, a laser welder, so on and so forth, we do only offer those in Siemens controls. Obviously, there's a lot of development for those special technologies, and we don't necessarily offer both control options in that regard. But standard machines, Fanuc is the standard.
Kind of a general question requesting that you talk a bit more about scenarios where you think live tooling is underutilized.
Um, you know, a component that requires additional drilled holes um, is very common to go put that on a mill. No problem with doing that. I think there are opportunities to use live tooling, and I think some people get scared away because of the cost of live tooling and the maintenance of live tooling. Um, Especially if you're talking about a straight or a 90-degree one-to-one geared live tool, very inexpensive solution. Um, where there are more opportunities are perhaps on utilizing a live tool to put in a keyway of a flanged part. We've done this on several applications, and it eliminates the need for that special purpose type solution. We've had a solution where we've actually done an internal spline with live tooling. And there's just a lot of clever live tooling solutions out there. And, if you get something more exotic, let's say just for a keyway cutter, maybe you're spending 15 grand, whatever, for a live tool head. But if that eliminates the need for a broach machine and the broach tooling, I think you're ahead. So I would always challenge customers to think about combining processes that could be put on a live tool turret.
All right, to our audience members, just one more heads up that this is your chance to ask questions. We just have a couple of more in the queue right now, and let's go with this one. You seem to have a number of automotive solutions for shafts, but what about job shops? Do those solutions fit for job shops?
So, I got to concede that if we're speaking with a job shop that has one or two machines that's doing onesie twosie type work, that's really not the space for our equipment. That being said, we by all means are not strictly a high volume automotive supplier of machines. Last week we got an order from a customer who only runs 12,000 parts a year, and that's spread out over 11 different part numbers. And there are other examples out there, but what we bring to the table that for customers who do have, let's say, batch sizes of 50 at a time or have redundant part numbers coming through, once you've set up the part, it's always great to come back to the machine, load up that conveyor, and walk away. It means your green light's on, your spindle's turning, and you're making parts. The average Emag load unload time is only 8 seconds. So if you can load up a carousel with 20 parts with, again, a 20-minute buffer, that means your operator is doing other value-added work on another machine, whereas perhaps previously he has to stand by, manually load a machine, and be dedicated to just there. So in today's day and age, especially as we've just got through this whole crisis, I think a lot of employers might be asking their questions, do I want to bring all these people back? Is there another way which I can bring in a more automated solution, maybe without investing in third-party automation, and still make good parts and the same quality I expect, but with the same manpower? And I think this is where Emag comes to the table with a lot of smaller shops that we previously didn't have visibility with.
All right, Kirk, I think we've got just one more question here. For all of these other technologies outside of turning, how do you support them here in North America?
So our headquarters here on the screen right now is Farmington Hills, Michigan. And for the vast majority of our machines that we bring into the US, they come through the shop, means we do the engineering here. We work with local work holding tooling people. We do all of our runoffs here. And support everything out in the field. And the vast majority of those machines, turning and simple grinding, follow that model. Where we do get into the other technologies, induction hardening, laser welding, we do have dedicated technology centers out of Europe that do that project management and engineering directly. Sometimes, we don't have the metallurgical demands to perform on those other technologies, and no doubt the deeper you go into the technology, the more specialized it is. So we do a lot. Once those other technologies come here to the US, we are trained up and we are the first line of defense on the service and support side.
Excellent. I think that does it, and that concludes today's presentation. I want to thank Kirk and Emag for making this webinar possible. And thank you to everyone listening in. You should receive an email with a link to the recording soon. I'd also like to invite you to our next Modern Machine Shop webinar on data democratization and unlocking the value of Industry 4.0. Visit mmsonline.com to register for that webinar, which takes place next Tuesday, June 16th at 2 p.m. Till then, thank you for your time and enjoy the rest of your day.